There, officially starting the recording so I can say to the YouTubers, the Roomers, and the Zoomers, happy garbage day. On this lovely, freaky 80-degree day. I don't know what's up with that, but I know for sure that it's not going to be 80 degrees when we take our kids trick-or-treating in 2 nights. That's what I know for sure. It's going to be snowing by then, probably, because that's what happens. So, anywho, our first task then is formative assessment number 4. And Vladimir is going to walk us through that. I'm going to man the doorbell, so you don't need to worry about that. Take it away.
Thank you, Lisa. Hi, everyone on Zoom. Hi, everyone in the classroom. Today I feel that I cannot talk loudly. So if you cannot hear something, you just can raise your hand and ask for additional comments. I don't feel like 100%, but I feel good.
If you're feeling sick, I can take over.
No, I don't feel sick. It's just like my voice is like not as the usual excitement level.
Project from your diaphragm.
Yeah. I'm always like, hey, how are you doing? Let's do it. Today I'm just like, let's do it. So as Lisa said, today we have a lot of additional files because our goal is try to help you understand question 1 especially, because reading your answers, most of them were good, but I think that the answers were more related to the substantive part of what a random slope means than what Lisa was asking for, which is specifically how the V matrix changes when we have a random intercept versus when we have both a random intercept and a random slope. So we were talking about this, and she created a file that I think is excellent to understand this. And conceptually, I have some references for you to think about this, and then you will be able to see specifically in matrices how the V matrix changes. So that's awesome. Thank you, Lisa. And for questions 2 and 3, we also have a spreadsheet. So we will be talking about how to get the estimates. Most of you had these 2 questions, 2 and 3, good. I saw that sometimes the answers were good, however the code was wrong, so we can check both things, okay? And I also have references for that. So first of all, thanks to the student in Bayesian psychometric modeling, because yes, I'm TA in that class too. For those who are taking that class, you know what I'm talking about. One of the students said, could you please share your references when you are checking our answers for formative assessments? And I say, yes, of course. So for this class, most of the time when I have a question, I ask to Lisa questions. I attend office hours and I try to express my questions, and we talk. But I also like to check slides, examples, and class records to try to get like a general idea of what the answer of my questions are. So for this specific formative assessment for question 1, I like this video, Lisa's video, of course.
Oh, you can't play the video, I don't think.
Sorry, just to show you, because I think that this is public, right?
It is, but I might get in trouble for copywriting myself.
Okay, don't worry. And I think that we could share this list, because if you check these references, I think that you will be able to understand what we will be covering now. So
I can post it later.
thank you. This is from our class next semester, Advanced Longitudinal Models. However, the first homework of formative assessment was a list of questions based on this class. So I think that formative assessment was pretty helpful to understand some of the things that we are talking right now, especially related to random effects. So that was the introduction. Sorry for that. Too long, I think.
It's okay. You're good.
Thank you. Let's go back to our questions. So, question 1. What's the difference between the marginal implied or model predicted V matrix of variances and covariances when random slopes related to change over time are included in a model versus when only a random intercept is included. I would like to hear some opinions first. What do you think about this question? What could be the main difference in the V metrics when we have a random intercept model and when we have a random intercept plus a random slope model?
I was thinking about the G matrix component. That would be different in terms of the argument intercepts.
For sure, yes. Yes, Ahmed, thank you. And I think that most of the answers were related to how the G metrics changed when we have a random intercept only and when we have both random intercept and random slope. And that's true, the G metrics will change. But what do you think is, what do you think the implications for the V metrics are in this case, after including a random slope? What are we doing, or what are we introducing in our model? I'm looking for one key concept, but I think that that's a hard concept. So let's go step by step. When we introduce a random intercept in our model, what kind of pattern of variance do we have in our V metrics? Because we know that in the G metrics we will have one component, right? Random intercept variance specifically. In the V metrics, what's the translation of that? What kind of pattern do we have in our V metrics when we have only one random intercept or random effect in our model?
It should only affect the diagonal?
Sorry?
It should only affect the diagonal?
Can you elaborate on that, please?
Skin and nails, like just hanging on the edge of a cliff here.
Yeah, no, that's okay.
Because
Don't
I think
worry.
the diagonal has the variance.
Exactly.
And then the off diagonal has the covariance. And you
Yes.
don't have covariance if you only have one random effect. Because the covariance is if you have two or more random effects.
In the variance, we have, in the diagonal, we have variances. In the diagonals, we have covariances. Yes. And I think that to answer this question, and that's why I wanted to share this, because in lecture 5, slide 8, you will find this.
It's open somewhere.
Yes, here it is.
Can you
Here.
also tell them what kind of R matrix you have?
Oh.
Because I had a few questions about that.
Yes, of course. I think that this will help for both purposes, because in this slide, you can already see what the V matrix would be and what the R matrix is, after including only the random intercept in our model to capture person mean differences, which are constant, right? So, what kind of pattern of variance do you see here in the V matrix? Is that changing over time? No, it's constant, right? Now, as Lisa said, after including a random intercept in our model, what's the structure of our R matrix? Time-specific R matrix. Is compound symmetry? What do you think? Is the R matrix, the structure of the R matrix, compound symmetry? Is it or isn't it?
Well, if there's a random intercept, it's the diagonal, is what they call it. But if there's no R random intercept, then they call it compound symmetry. Is that
Oh,
right?
okay, okay. Be careful with that.
Okay.
Because this kind of a structure in the R matrix, this is called independent structure. We have only one variance, and that is the same variance over time, and we have no covariances between time occasions or between occasions. This is because we are assuming in our model now that this occasion, the time-specific occasions, are correlated because of they are part of the same person. They are different measures of the same person, and we are saying that those things, those time-specific occasions, are related because they belong to the same person or to the same unit. in this case. So here now, well, this can be changed in longitudinal analysis.
Yeah, you can choose what kind of R pattern you have. I was assuming this kind, which is either independent or diagonal or variance components based on what your software you're using is. So like R is independent or diagonal, but then B is compound symmetry when you add the G matrix contribution to the random intercept variance.
Exactly. Yes. So right now in our R matrix, we'll have only one number or value for the variance, and that's the same over time. This is an independent structure. Now, in the V matrix, we have a compound symmetry structure. Why? Because our variances, you can see that they are the same thing. Whatever this value is, when you sum your random intercept variance plus your residual variance, that number will be the same over time. So we don't have time-specific heterogeneity, okay? Now, this is one half of the answer of question 1, because now, if you go to,
It's in there somewhere.
yes, so here you have the same thing, but differently, with the components for each. But you can see that the predicted variance per time in the random intercept only model, this is the variance, this is the predicted covariance. Now, the V matrix will change once we add a random slope in the model. So I think that question 1 was specifically related to this component here. Let me make it bigger. To this component, or maybe this whole blue box. Why? Well, I know what the answer is, but let me ask you, sorry. What do you see here? What do you see here? Before in the V matrix, variances were the same over time. So the pattern of variance was homogeneous. However, what do you see now?
It's time dependent.
It's time specific. Variances are time specific, yes. So they change as a function of time with what kind of pattern?
Quadratic.
Quadratic, exactly. Yes. So now, I was talking with Lisa about this because I thought that this pattern was an option, but not in this model. This is what you have when you introduce a random slope in this model. I mean, we couldn't change this, and I thought that we could, but that's not the case for this model.
Yes, if it's a linear slope, then you're introducing heterogeneity of variance along the predictor, the slope is 4. And it's quadratic, it has to be, because of the square term comes down.
Exactly. Must be quadratic. So, to answer question 1, we were looking for something like this. When you have a random intercept only, the variances and residual covariances will be constant in the V matrix. And I know that many of you answered that random slopes will capture slope differences across people. That's also true. But to me, that's something more substantive than related to the V matrix directly. So, if you wanted to answer that, I would say that we were expecting something like in the random intercept only model, you have a constant pattern of variance and covariance. However, after including the random slope in your model, the variances will have a quadratic pattern of heterogeneity. And the covariances will also change as a function of time. And the relationship, because here we have the covariance between random intercept and random intercept and random slope. Sorry. Do you want to add something?
Yeah, I say it's time dependent. Some folks said that it's person dependent, but that is not the case.
Yes.
In these models, we're assuming homogeneity of variance across people. It's heterogeneity of variance across occasions.
Yes. Yes. Let me repeat that for the recording, because many of the answers were relating this pattern of variance and covariances to person. However, we are assuming homogeneity of variance across people. We are assuming heterogeneity of variance across time. That's why in the matrices here, this matrix is representing time-specific occasions. So in this case, we are assuming that we have 4 occasions. And now, do you want to share the Excel file now or after
I'll
that?
talk about it later.
Okay, okay. With that file, I think that you will be able to understand better what's going on, because conceptually I think that this works, okay? Just looking at these slides, you can get the idea of this heterogeneity of variance and the quadratic pattern of change. But I think that the Excel file will help you to get like a more general idea. Now, you can use this formula, and I did it to get the time-specific variance. So that was pretty helpful too. Now, yes, sorry.
And then I think Ahmed also has a question too. I'm not sure which of us had our hand up first.
You're first.
My question is, so I think I'm getting confused with like in chapter 3, we were looking at the model for the variance, and we were looking at how you can create like kind of heterogeneous variances just in the R matrix through like AR1 or a time lag, or like any of the models could have a homogeneous version with variances or a heterogeneous. So is this like, would you ever do both, or is this like an alternative way to explain the relationship between the variance and the covariance, so that you would never use those two models at the same time? Like you could use the R-only matrix to try to explain the relationship, or you could add a random intercept and a random slope, and it might kind of approximate the same thing, but it's like two ways of getting at the same goal.
That's a good question. Let me repeat it for the recording. Can we have, and I think that this is a good question for all of us. The summary of the question is, do you think that we can have something here in the R matrix in this model right now? Do you think that's possible to add some additional time-specific relationships in the R matrix? Or do you think that we will have models for the R matrix only and models with G and R matrix like two-side different things? Do you think that we could combine both approaches? That we could have something in the R matrix, some kind of ACS, alternative covariance structure, plus our G matrix with the random intercepts to capture person mean differences? Do you think that's possible?
If I remember right, this way partitions the variance.
Yes.
But the ACS, I mean, I guess it's kind of partition, but it's all in the same matrix. So maybe you can't combine them because you put all of the person variance in the G matrix.
Yeah.
So it's the only thing left in R is the truly residual variance.
It's the time-specific residuals.
Times
So, in this model right now, yes, we are partitioning within and between things, right? We know that in the G matrix, we will have the between person mean differences in the intercept or with respect to the fixed intercept. And now the R matrix will contain the time-specific residuals. Yes? But we can actually introduce an additional pattern of time-specific relationships. We can, because this is not like in cluster multi-level modeling. And maybe Lisa can help with that. Yes, please.
Yeah, so,
Because that's an important question.
yeah, so the question was, if I come back over to where the recording is, so you don't have to repeat my repeating, can we have like heterogeneous variances in this R matrix when we're using a G matrix? Yeah. Yeah, that's actually in chapter 4 is one of the choices. So the way that I would think about this is the R matrix structures that are heterogeneous, like they come in, like it's all or nothing, right? Like you have a different variance for each spot or they're all the same. The benefit of the random effects version of this, which is, let me find that slide again. The benefit of the random effects version of this, almost there, here we go, is that you're creating a function by which the variances differ. So you don't have to have a separate variance for every single possible time value. You can have unbalanced time and still have this quadratic pattern because you can like interpolate or extrapolate. I'm not sure what the right word is, but you can figure out because based on where the line is going, where your dot should be. How's that? Interpolate? Math people?
It sounds.
I don't know. Extrapolate or interpolate. I can't decide which it is. So like on this slide, there's an example where the second person has a different set of time values, and their resulting V matrix would be based on their time values, but it's based on these common ingredients in terms of what everyone's residual variance is, what everyone's random intercept variance is, what everyone's random linear slope variance is. So you can combine them. Now the issue with heterogeneous variances in R is that to some extent they're going to be redundant with what G is trying to do, because random slopes introduce heterogeneity of variance already. So then you're putting more, and it's got to figure out like which source of heterogeneity is going to go to which spot, and it's going to mess it up in some cases. So I don't recommend letting all the residual variances be different. Like maybe one or two need to be, that would be all right. Like the question then is, can you pull that off in software? Judge's ruling, interpolate within endpoints, extrapolate outside of endpoints. Okay. I think I mean interpolate then. Unless the line keeps going, and then I mean extrapolate, but one of the two. So, all right.
So, I understood Rebecca's question in a different way. Like, could those zeros in the R matrix be like fixed numbers instead?
Yeah. So we could throw in like an AR1 correlation into R, in which case these off diagonals would be some function of that AR1 correlation. So they would build a covariance in here that would be autoregressive in pattern. Yeah, you could do that. We did that at the end of the chapter 5 example, and we did that at the end of the polynomials handout too.
Mm-hmm.
In 6a, we tested an AR1 correlation to see if that would help, and it didn't happen to in that case. So yeah, you can mix and match across these two approaches. There's a few rules about what you can and can't do though. Like, let me find these matrices again. So for instance, if you have this one, you can't have a compound symmetry R matrix and a G matrix with the random intercept in it. That's completely redundant. You're saying there's two different sources of constant variance. You figure out how to parse those apart. Like, you can't do it. So there's a few instances in which like redundancy would be the issue, and you'd probably figure that out by getting dots in your output or angry convergence error warnings, all that. So.
Is that the reason why we delete the last lag too, if we're trying to do, because we can't have nothing to predict?
Yes, so if like for the saturated version of this, like you can't have this be completely unstructured, because then you're trying to get one more thing out of it, it's under-identified. So that's why we shut off this last covariance, and we say that one's only due to the random intercept, and then the others are additive beyond that. Yep. Okay. All right, I think that's question 1.
Yeah. No, that's hard. That's
No,
a
this
hard
stuff
one.
is hard. I can't tell you how many years it took me to understand how these pieces fit together, especially as someone whose matrix algebra leaves a lot to be desired, because I don't have an intuition about this stuff. I have to like brute force it. So speaking of which, the spreadsheet that I put up just a little while ago, I built this myself when I was writing chapter 5. So this is the chapter 5 data. These are the model parameters that I got out of SAS, and then I literally just tried to build everything. So here's the Z matrix for 2 hypothetical people. Here's the G matrix that those parameters do. Here's the R matrix. And then the first step was Z by G, and then there's Z transpose, and so then I tried to put those together, and then I added the R part in, and then I tried to make sure that the rest of the math worked with what else I got out here. So if you're someone who likes to tinker with numbers to feel better, I would recommend this as another resource.
Yeah, that's awesome.
So, but this is the one that I built for
Yes.
you, though.
Yes.
So, get that one back up. Okay. All right, I'll get off the podium now.
No, thank you so much, Lisa. So yeah, so 2 takeaways, I think. First, the key concept here when we talk about the V metrics is heterogeneity of variance. That's what we are introducing in our V metrics. Yes, across time. That's the second takeaway. We are not talking about people, but time. And the specific pattern of that heterogeneity of variance is quadratic for this model. Then when we add a random slope for the quadratic fixed effect or the quadratic time, that's quartic, right? You will see that later, yes. So now, additional questions, something that you would like to hear again about question 1? Do you feel better about this one? Great. I see people nodding, so thank you. Now, to cover question 2 and 3, I would like to use this Excel file here.
Example 6A is also published for question.
Yes, exactly. Why I'm talking about example 6? Because here
It's up there somewhere.
6A.
should be
6A.
here.
I know, I have
Yeah, I
18
cannot
things
see
open.
it there.
That's B.
Ah.
This is A.
Was a word. I was looking for the PDF.
Yeah, no, I'm sorry.
Thank you.
I'm guessing
Page
you want.
8, 9.
page.
8 and 9.
Okay, you can.
See, he does know the page numbers.
Well, he knew what he was gonna do for today, right? That's the thing. Here,
yes.
that one probably.
Yes, exactly.
Okay.
Yes. Thank you, Lisa. I was talking about these pages in example 6A because the answers were here, at least for the part of the code. So this was interesting because, as I told you, some of you had the answer correct, but the code was incorrect. So maybe we could check both things at the same time. Okay? So specifically for question 2, what do you think the predicted here? What do you think the predicted outcome at time 4 would be based on this model? You can give me the predicted outcome, or you can give me information about how time would be introduced here. Comment?
10 plus 12 plus 8.
Times?
10 plus 12 plus 8.
Why 12? Yes. Why is 12 here?
Because it's time 4.
Because times 4 times 4 times 3 is 12, and here
4.
times is 4 again. This is 16. No. Yeah, 16. And this is 16 times 0.5, which is 8. Then you add all of those things, and you get the predicted outcome, which is 30. Yes, Taylor, thank you, 30. Here, example 6A. So yeah, here you had that answer, specifically for time 4. So the first time that I took this formative assessment, I was thinking that Lisa was asking for time like not center, so I subtracted 1. That was my bad. Here, if time is 4 and we have time, you can plug 4 there directly. So that was the answer. Now, in terms of code, to get predicted outcomes, what's the meaning of this? In Stata, or this one in Contest 1D in R?
The intercept.
The intercept, yes. Why do we need the intercept to estimate a predicted outcome? Silly question, I know, but why?
Part of the model.
Because it's part of the model, it's part of the equation, right?
It's the starting point. But okay.
It is. When we talk about predicted outcomes, please consider that one of the parts of the predicted outcome is the intercept, okay? So I saw that some of you forgot this part when you were showing your formulas, and that would be incorrect in your software. So pay attention to that, please. But the other parts, most of the time, were correct. So here, you are introducing 16 because this is time squared. So 4 times 4 is 16, and this is just 4. So those numbers in the software are being multiplied by whatever the fixed effect for that term is, okay? Now, question 3 is related to this. Question 3 says, how does the model create a predicted instantaneous linear slope at time 4? And now, thoughts, comments? there is one sentence that I'm looking for. A complex one, I know, but Lisa repeated this many times last class about the half rate of acceleration or deceleration, which is the fixed effect of quadratic time. This term, we know that right now this term is half the rate of acceleration or deceleration of the mean linear rate of change. What do we have to do with this slope to get the instantaneous linear slope at any time? There is a rule. Yes, Erika, we must multiply it by 2. And the explanation for that is here in lecture, let me consult my references. Lecture 6, yes. Thank you, Lisa.
I know, at least I know which lecture it's.
So here is the explanation for that. You need, whatever that fixed effect is, you need to multiply that by 2, then by time, and then that's added to whatever the fixed effect of time is. That, in terms of software, is translated into this part here at time 4. Again, I saw correct answers, like conceptually, but in terms of code were some errors. So now, what do you see is the main difference between this line and this line ahead? Sorry. In both, we are talking about time 4, right? What's the main difference? We are dropping something, right? Exactly, we don't have the intercept because we are talking about the slope. So, please pay attention to this, because here, this is 1 over time, because the fixed effect of time won't change when you want to get a slope at a different time point. This slope will be always the same value or the same number. What we want to know is how that main effect of time will change at a specific time based on the moderation of the interaction term, which is time, because we are talking about interactions here at the end of the day. So here you can see again that we have 8 here, because we are saying, take please whatever the fixed effect of quadratic time is and multiply it twice time. Time is 4, 4 times 2 is 8, and here we have the answer. In R, almost the same thing here. So now here is more explicit, I would say, because here you are saying, don't consider the intercept, please. Just consider the time slope and apply whatever the change at that time is. Okay, so to close this, I would like to show you this, which is like the key answer. Because with this information, we know that the fixed intercept was 10, the linear effect of time was 3, the quadratic effect of time 0.5. If we were interested at time 4, we just had to take, let me make this bigger.
Yeah, the formula will improve in size.
Oh, yeah. But we know that we must combine the fixed intercept here. We must take the multiplication of whatever the fixed effect for time is at time 4, plus the quadratic effect of time. That's the quadratic effect. There we are multiplying time by time. This is the predicted outcome, and this is the predicted linear slope. As you saw before, we are taking whatever the main effect of the main effect of time is, and we are adding the half the rate of acceleration times time twice, times 2. So that's what you needed for those 2 questions, okay?
Just to make sure, this is for a specific person, right? For one person.
Yes, exactly. Well, for the group of people with these values, right?
Anybody with time 4.
Yes.
This is their
Oh.
expected outcome. There's no
Yep.
random
Because we
text.
dropped the subscript I thought that it's a specific person.
No, it's for anybody at time 4.
Yes.
Okay.
This prediction just consider people or units with time equals 4. If you change this to 5, for example, so now these two predictions would be specifically for people at time 5, and so on. So now, do we have 1 minute? I don't think so. Oh, it is 1:11. I think that we are done. Because I...
Time limit, but okay.
Yes, questions or additional comments, things?
So when we are calculating the predicted linear slope for a specific occasion, we don't have to take the effect of time squared. That's only for predicting the outcome. We're not squaring time for the slope. Is that true?
No. Yes.
That's true.
Yes,
Okay.
that's true.
Okay.
Yes, that's not the case. That's true. Yes.
That's where I got it wrong then. Okay.
Yes, because again, when we are predicted something, if you look at the model here, when we are predicted something is when we are taking this time square. It is the same. Well, here you can add an interaction in the model, or you can add time square directly as we are doing here. The result is the same, but when we are predicted something, we are considering time square. When we are predicting linear slopes, we are taking twice whatever the half rate of acceleration or deceleration is, times the specific time we are interested in. Okay?
It's because the slope is derivative, so we get derivative of time squared. It's 3 times time.
I think so. Yes. Yes. Great. I hope you had a good time with this. And if you have any additional questions, you can attend office hours or email us. So I hope you have a good afternoon.
Thank you.
Great. Thank you for your time.
Yeah, where's my applause? I do this every damn day. Woo! All right. Hello, Zoomers. I'm back in front of you. I'm off my phone now, but I was watching your chat. So yes, take-home message: if you are predicting an outcome, square time. If you're predicting a linear slope, multiply it by 2 instead. That's it. Got to get my chair back. I'm too short otherwise. There we go. Also, I wanted to reiterate why we called the linear slope the instantaneous one at that point. So let me put this back to 4. So if I solve, so if I know that these are my new conditional, I would call this conditional outcome and conditional slope if time is 4, then I can plug those into here. The quadratic slope would be the same because it's unconditional. In this model, it's the highest order term. So then if I try to verify my math, like this is set up to be specific to time 4 as the 0 value. So I would enter 0 here, and lo and behold, my predicted outcome matches what it is above, and my slope does too. So if time is 0, the quadratic drops out, and all you have left is the linear term in terms of what builds the linear slope of time. So this is up on the website. The V-matrix thing is up on the website. Any other questions on that formative assessment or any of the stuff that we're reviewing? No? Zoomers, how are we doing? Thumb check? I'm shooting for either sideways or slightly above sideways. That's my goal. Okay, fair. All right then. Save that. Bye-bye V-matrix. Let's see, yes, so in example 6, just to remind you, the end of this, so this built all the way up through random quadratic as a means of review. And then the next model that I tried was, is there any residual correlation left unmodeled in the level 1 R matrix? So then you can change R from something that's not diagonal into some kind of pattern. And I have seen this be necessary, particularly in longer designs. So I mentioned a study where it ended up being a fixed quadratic random linear model for change over 30 sessions of a task. And they also needed an AR1 correlation in the R matrix because sessions that are closer together still had an additional relationship that wasn't being captured by the random effects over in G. So that's something you would want to check, I think is just a good housekeeping kind of thing. All right, let's see then. Are we ready to talk polynomials? No, piecewise. We just talked polynomials. Pieces? Linear splines? Some of you are very excited about this, right, Alex?
I am.
People who do single case designs and intervention designs. Oh, someone else just perked up. What? That's you too? Are you excited? Yes. Basically, when you change what is happening over time and you want to see what happened as a result of your efforts, that's where we would do that. So let me go find the piecewise models here. Okay, so picking up on slide 25 as reviewing the end of the polynomial section of lecture 6 here. So my intermediate summary, Nikki likes these too, thank you, or 10 does rather. Modeling within person change involves specifying slopes related to time. Now that is a very deliberate choice of wording on my part, because just sticking time in as a predictor is making a statement that you expect change to be linear. Sticking in time squared creates quadratic, but there's other ways that you can have predictions that change over time. So we're going to get into some of these alternative models. So with respect to the fixed effects, their job is to reproduce the average trajectory. So what kind of line or bendy line is best going to reproduce the saturated means? That's the question. Is it straight? Is it bendy? Is it continuous? Is it discontinuous? Those are the questions we would focus on. With respect to the model for the variance, what kind of individual differences in change do we see in our data? How many sources of random effects do we need? Do we just need an intercept, give each person their own starting point, and then there's parallel change? Or do people change differently? And do they change differently in each aspect of the trajectory? So they might need their own linear slopes. Do they need their own quadratic slopes too? That's an empirical question. What's happening then behind the scenes is that those random effect variances and covariances are building a pattern in which the variance changes over time in a particular way, and the covariance changes as a function of which two occasions you have. And what's cool about that is that these are relatively parsimonious models, that yet they can make predictions for any observed value of time, because we're talking about functions rather than treating time as discrete. So in the same way that like you can have a saturated means model where you have a separate mean for each occasion, that fits perfectly, but it's not very parsimonious. The alternative would be any heterogeneous variance model, like in terms of the R matrices, where you have a separate variance for each occasion, and that's not very parsimonious. We're heading towards models that build functions that allow differences over time, but we don't have to have a separate parameter for every single unique value of time, because that may not even be possible if there's not a lot of overlap in when people have been measured. So linear, quadratic, cubic is one family of options. The next one that we have is what I call piecewise slopes. So piecewise models is the idea that you are dividing time into sections that correspond with what is known as a breakpoint, a change point, or a not point. Those are all synonyms. So this is useful in examining changes and intercepts and slopes due to things like policy. So there was a student once who was looking at, in the business school, looking at the effect of repeal of blue laws, I think in Minnesota maybe. It used to be the case that you couldn't go shopping on Sunday. Like it was just against the law, like literally stores were closed. This was, I don't remember when it got repealed, but to me that's insane because I spent every Sunday of my childhood at the mall, pretty much. And so I can't imagine not shopping on a Sunday. And they were interested in the economic impact of repealing this law. So it is very much like before, after. If you were lucky enough to collect some kind of baseline data before COVID hit, you've got a nice before and after. The key idea, though, here is that these particular versions of these models are for when you know when the breakpoint is. So I once had a student ask me, who was in developmental psychology, oh, cool, could I do like before and after puberty? People are laughing. I said, sure. Do you have a date in your data set as when puberty happened? Discreetly. Like all of a sudden your voice drops, you get body hair, you start being able to produce children. When did that day happen? You're like, Exactly, that's the problem. So transitions that are more amorphous do not lend themselves to these models. There are alternatives though. So if you throw the word latent in front of it, then there are models in which you find empirically where the breakpoint is that would describe a trajectory. And then you can throw the word random latent in front of it. And guess what that does? Individual differences in where the trajectory changes. So for something like the onset of puberty or the onset of terminal decline in an older adult context, there are models that try to find the point at which things start changing in terms of how the trajectory shifts, and you can have individual differences in that. Those models take a ton of data. Like you have to have a really long time series and a lot of individual differences to pick up that stuff. I've never been successful in getting one to converge. But I've done the fixed version. I have an example of that if anyone cares. So these models are simpler because there's only one breakpoint. You can have multiple breakpoints, but there's only, it holds for everybody. It's a fixed effect, and it's not something that's being estimated. So here's an example from one of my earliest classes. This was a student who was doing a multiple baseline intervention type design, and they had a 5th grade classroom here. So the context was improving student responsiveness during class when it came to being able to read out loud and answer questions and stuff. I don't remember what the intervention is. I'm not sure it's relevant. Can I just make something up?
Sure.
They threw candy at them. How's that? Right answers got candy. There's your intervention. So they're like, do, I'm just going to collect a bunch of data over a 2-week period or so where I didn't throw any candy at them. Then I start throwing the candy, and lo and behold, oh, they're more responsive. And they continue to become more responsive as they realize that every time they answer a question, they'll get some candy. And then they ran out of candy. Wah, wah, and they start sucking again. They don't want to play. Then they brought the candy back, and now they're better again. How'd I do? Multiple baseline intervention design?
I mean,
He's like, no.
well, I mean, it looks a bit more like a reverse.
There's words for this, I'm sure. Yeah, start sucking again is my technical definition of the drop in intercept that we observe here.
Well,
But
the only thing like with a multiple baseline is it's like kind of often used like when you can't truly reverse necessarily. So like with learning, for example, like you're not going to forget what you like reading.
Right.
You don't just forget, like you can't go back.
yes, after you've been treated, you can't become untreated in most contexts.
Yeah.
But I think the outcome in this case was like a responsiveness indicator
Yeah.
as opposed to a skill indicator.
Yeah.
And that can change.
Right.
Right. This is something that I observe twice a week. Individual differences in responsiveness that fluctuate throughout the semester. How's that for a real world example? No, Zoomers aren't laughing with me. I'm trying. I really am. So-
Internet connectivity is a big thing for being on Zoom. If you're trying to respond and you're like, hit the mute. What?
Yes. Positive reinforcement for engagement. It's not you, it's Zoom. Yeah, I know Zoom is kind of demoralizing, but at least you're sitting in your pajamas attending class, right? Or you're getting laundry done, or your cat's being fed, or whatever, you know. It's a good thing for multitasking in life, I think, or saving gas, or whatever. But the way I would think about this particular example is that during this baseline, we would not expect any change over time. You're just trying to get a sense as to where the kids are at. I would expect a discrete shift potentially in intercept and in slope, because all of a sudden they jump up. So I think of that as a jump, is like how that's the language that I use in the book, and then a difference in slope after that point, followed by a negative jump. Can I say that? In the same way that we have negative acceleration, a negative jump for a decline. And then a change in the slope as well, and then an increase and a change in the slope. So like this picture could not be more perfect, like to illustrate what these models can do. So that's why I have it in here. This also works, by the way, if you have a, what is it called, like a delayed start kind? There's a word for it.
That is a multiple base.
Staggered baseline something? Like where you deliberately like start someone later so that it's not just like that day that you can say the effect is due to, but it shows up no matter when you are. That can be a level 2 person predictor as to when they started. so that then you can control for when their baseline was and see if there's any difference based on if they started on, September 30th versus October 5th or whatever. You can do that as well. So here's another example. This requires me to put on my health psychologist hat for the time being. I have a lot of hats. You have to when you play with other people's data. That's the nice part about being a quant person. It's like if you can't figure out what you want to specialize in terms of social sciences, become quant, because then you can play with all kinds of data. So that was, elementary education and reading and teaching strategies. Now we're talking about cortisol. Yay, cortisol. Okay, so now I have a cortisol person in the house. I'm going to try and get this right. I know very little about cortisol, but what I know is that it spikes about a half hour after waking, and then it slowly declines the rest of the day, and that if you don't decline very much, that's bad. Like a normal rhythm is like very like this. I'm out of words today, apparently. So I was working as a postdoc, and folks down the hall were studying cortisol, and they didn't know how they wanted to model it. And I thought, well, we can do piecewise models. So I brought them this technology, and I believe they're still using it. So this is an example of within-person time as what this x-axis would be. So this is unbalanced in the sense that the subjects were given the instructions to chew on a piece of cotton and then stick it in a tube to mail back in when they woke up. Then 30 minutes after, whenever that was, whenever they ate lunch, and then before they went to bed. So this is not balanced time, even though there's 4 occasions, right? I've asked this question before. Vladimir, when's lunch?
5 p.m.
5 p.m.? I'm sorry, that is incorrect. That is dinner time. But they didn't have a dinner observation here. So yes, lunch for me, because I teach at 12:30, is at 11:15 at the latest, right? Because that's what I need to get to campus. And if I don't eat lunch before I come to you, it's not going to be a good day. I'm already having word finding problems, and I'm fully caffeinated and fed, all right? This is about as good as it gets. But if you wanted to set up, Kendall agrees with you, by the way, lunch is at 5 o'clock. I think it just depends on when you wake up and when you go to bed, too, because you got to, like, manage your energy levels through food and whatnot. So in this model, they call this first piece the morning rise of cortisol, like they had a name for it. And the latter piece is an afternoon decline. So the 2 predictors, this is SAS code, but you can probably follow it regardless. The way this is set up is that I decided to make the first occasion the intercept. So the first piece, this is a new time-related variable in purple, and the second one in orange is initiated to 0. And then the morning rise is captured by the purple one. It's the distance in time between whenever the first occasion was and the second. So 30 minutes was the target. What actually happened would be based on timestamps of when they opened these pieces of equipment to go spit in them. The second piece is not awake yet, because the second piece is in charge of the afternoon. So it stays at 0. Now, afternoon, the morning rise is over. So the P1 value here does not change. It stops where it left off, because then orange kicks in to take over. And so then orange is how much past time 2 are you at time 3 and then at time 4. So the code that I'm going to show you for my example is simpler in that I'm able to use integers because it's balanced data. You would need to do something like this to subtract between occasions to get the actual distance in time. And this assumes that you have a data structure in which time 1, time 2, time 3, time 4 are columns that go across all your rows. That way you can access them regardless of which particular occasion that you're on. Okay, Taylor, how'd I do? Do I get the health psychology thumbs up? Good. Okay, not great, but good. That's good enough for me. I can live with that. So this orange line, just visual inspection here, visual analysis, as it were. Does this look like it fits? It doesn't fit. You think of an idea of how I can fix it? Make it bendy. Yeah, I can have the second piece be a bendy piece.
So in occasion 4, why we did time 4 minus time 2 instead of time 3?
Because I'm tracking the total distance in time for this one slope rather than having 3 separate pieces. If I wanted to have a separate relationship between lunch and bed, then I would change this to 3, and I would need a third variable to make that happen. So you can think of, like, if you have as many pieces as possible, that's equivalent to saturated means in that case. Because it's like, if you can think of it as going from an intercept to the 1, to the 1, to the 1, right? The 3 slopes and 1 intercept would give you the 4 means. So it would be the same thing. However, in a design like this, there's not just 4 means that are possible. Right, there's the 11:15 lunchtime, the 5 p.m. lunchtime, and everything in between. So there's not an answer key that saturated means could give you with respect to what the right answer is for these trajectories. There's potentially, each person has a discrete set of 4 observations in terms of when their time is, and you wouldn't want to ignore that.
And for quadratic, we need at least 3 occasions in the slope that we want to be quadratic.
Yes, and this is an instance in which it would not be saturated because everybody has their own time value. So yeah, go ahead.
Not balanced data? No.
It's unbalanced with respect to the timing, yes. Unbalanced time is what I would call that. All right, so here's a generic model then, like if I were to fit this model. So I still have YTI, I still have beta 0, and they still mean the same thing. So that's beta 0 is a placeholder or a latent variable for how each person is going to get their own intercept. The intercept is still wherever I put it with respect to all my predictors being 0. So I have to think about that ahead of time. Gamma 00 is still the fixed intercept, so what's expected based on the trajectory on average. U0 is how far off my intercept is, so that part hasn't changed. But now I have this called slope 1 and slope 2. So beta 1 is how each person gets their own morning rise, so to speak. There would be a fixed linear slope on average, and then an individual random deviation from it. And then slope 2, I can do the same thing. There's a fixed slope and then a random deviation from it. So the structure of this looks exactly the same as the quadratic model. The difference is in these slope 1 and slope 2 variables that are being input into the system and the patterns that they create. So these are 2 different linear slopes. These models are also called linear splines for that reason. That's a synonym that you'll see.
Could you end up having more than 2 slopes per person?
Yeah, data permitting.
So what would data permitting?
Okay, so there is a rule for this. For fixed effects, the number of fixed slopes that you can have related to time is n-1 in terms of the number of occasions, because you have a fixed intercept already. So if you have 4 occasions, that could be 1 intercept and 3 slopes, or it could be 1 intercept, 1 linear slope on the morning, 1 linear slope in the afternoon, and 1 quadratic slope in the afternoon. Or it could be, whatever configuration, but just you'd have 3 if you have 4 occasions. If it's unbalanced data, you could technically get away with more than that, but I think it would be difficult to explain. For random, the rule is n-2. So random slopes related to time, its number of occasions per person minus 2, because the 2 you already have are the level 1 residual variance and the level 2 random intercept variance. So it's a question is what else do you need that's related to time? So I need 4 occasions to fit this model because it has 2 random slopes related to time. All right, other questions? No, we're good? Let me show you a completely atheoretical example of this. Because just like quadratics, they can be used to solve problems, even if they don't necessarily make sense. So this is the trajectory for our response time data we're going to bludgeon to death, starting in example 6a. So this is the right answer with respect to the average pattern of change. Now we approximated this with the quadratic trajectory, which looked somewhat decent, but it didn't fit. We tested that by including extra contrast to literally fill in the gaps of the trajectory, and those extra contrasts were significant according to a multivariate Wald test. So an alternative would be something like this. Instead of morning rise, I'm saying this is an early practice effect, and then after that it diminishes into a later one. Is there anything magical about session 2? No. This is not pre or post COVID or pre or post blue law or pre or post intervention. This is an entirely empirically determined trajectory point to break. It just looks like two slopes to me.
But
Question.
couldn't it be theoretically important? Because I got so excited about this in the textbook because there's research in my field about the practice effects of preparing for like standardized language tests that have found that the biggest impact comes from just taking one practice test. And after that, like if you take a prep course for IELTS or TOEFL or whatever, it's diminishing returns. You don't get a lot of improvement beyond like, but if you take one practice test, that helps you so much, which is a huge leveler for students who don't have the money to afford to pay for like an expensive cram course. But if testing companies make just one practice test available for free, they can really level the playing field a lot.
Yeah. Yeah, so I'm not sure if the Zoomers held it. I'll repeat it for the recording just in case. Yeah, so if the context of this were taking a practice test before your college entrance exam, your language exam, your GRE, any of that stuff, there's research that suggests just doing that is a useful thing, and it's free and it's easy, and that more practice or more money thrown at the problem doesn't necessarily translate into more gains. How'd I do?
Or not as much gain.
Not as much gain. Diminishing returns, yes. Yeah, that could be answered with a piecewise model, but I would actually set it up differently than this. So I'm going to put a thumb, what is it? Put a thumb in that? Tack in that? I'm out of words today. What is wrong with me? Put a pin. That's what I wanted. Thumb tack. Pin. I was close. We're going to put something there to hold our place, and we're going to talk about that on Thursday. How's that? Question. Does that mean in the example of puberty, you could just state when you think it happens and hold it constant across all people? Yeah, I think reviewers would have a field day with that, would be my concern. If you used like age 12 and a half or something, that's going to be way off for certain people. I know there are scales that people use about like essentially asking questions about development and what you see and how far along the process, and they try to infer how pubertable you are based on that scale. Something like that might be more defendable. But yeah, to use these models, you have to be able to code in your data set where the breakpoint is, which implies you know the time that happened at. That's the main take-home point. So yeah, there's nothing magical about time 2 in my example, because they're going to make them do this task 6 times. But if every time you have to do this task, you have to spend more money and time, then I would certainly want to know where the diminishing returns are. Absolutely. So here's the coding that would create this model. So I have the orange variable and the purple variable here deliberately. So the solid lines show what this coding scheme down below is going to accomplish. So I've set up my first occasion, which is session, is my wave indicator in this data set. Set those both to 0. So that's where my intercept is going to be. The rules have not changed. There has to be one point in time where everything is zeroed out to become your intercept. Otherwise, your model is internally inconsistent in what it means. So I want to track the change from the first occasion to the second occasion with this one predictor. So session 2 is one more than session 1. Then I want it to shut off and let the other one turn on. So I don't drop it back down to 0 because I don't want it to go back to where it was. I shut it off where it left off. And so I code the rest of these 1. So the first slope is really just one difference. It's the difference between improvement from session 1 to session 2. Then from there, after session 2, I track how much time has passed relative to session 2 specifically. So that's why the purple piece is still 0 at session 2 because it hasn't gotten started yet. The second that we move off of session 2, then it turns on. And these are the integers that I can use in these spots because this is a balanced data example. Otherwise, I'd have to subtract how much time had passed relative to session 2 as a variable in my data set. And so then this tracks the change per session from 2 to 6. And so that's why I have named these slope 1, 2, and slope 2, 6. That way you can have a sense as to which regions they each cover. The dashed lines show you what would have happened had the other slope not been in the model. So if all I had was orange, this coding scheme would be like, you get to change once and then you're done. If all I had was purple, it is your first session doesn't help you at all. Practice doesn't start helping you until after 2. So these mean different things when they're in the model together than when they're apart, the same as most other coding schemes like this. So why this would be helpful, I'll foreshadow what's coming on Thursday next and then we'll let you go. Why this would be helpful is for designs in which what you want to know is how much change happened during one period and then how much change happened during a different period. So each of these slopes would be tested against a null hypothesis of 0, meaning no change during that period. Did you improve it first? Did you improve after that? Period. Now, if that's not your question, an alternative way of setting this up would be more useful. And this is what I would refer to the diminishing returns question. The purple slope is exactly the same. It starts after 2. That has not changed. The orange slope is the one that is different. And if you just look at these numbers, does this look familiar, this pattern? It looks like you just subtracted 1 and this is time. Yeah, that's what it did. I called it slope 1/6 to be consistent in my naming conventions, but yeah, we called this time last week. It's not different. The logic is that the orange slope is like business as usual. Like if nothing happened that was special after time 2, if your rate of improvement was expected to be the same all the time, that was what the orange slope would cover. So then purple is deviation from business as usual. It is how different the slope is after the breakpoint. And I think that gets at your question. So I would go with this way for any kind of design in which you expect change anyway, like that's just what you expect, and you want to know if they change more as a result of what you did. Like paying for an expensive practice session, or catching COVID, or going shopping on Sundays, or any of the things that would cause you to change more than you already were. How's that? So as you might imagine, these models have some equivalencies. It just depends on what you want to know and how you can make that a model parameter as directly as possible. I will show you that starting on Thursday. Dun dun dun. Stay tuned.
This is fun.
This is fun. I know, right?
Once you get past the beginning stuff, then you start to think about like how you can use it.
The nice part is that like for the next month, it's just going to be essentially be a review with just different kinds of slopes, but just trying to cement everything together still, because yes, this is hard. All right, anything before we call it a day? All right, thanks for being here, everybody. Excellent turnout today. It's very exciting. Let me know if you need anything. You can be working on your next homework, which is due Monday night. Bye for now.